gonna now consider real quick an from the lecture where we were supposed to use an inverse function rule. So the example is this one. I don't remember, it was the third or the fourth. The same for this function. We know that an inverse exists. Third, thank you. An inverse exists, so we can use the inverse function rule, and most importantly, we can actually be sure that the derivative of x in terms of y exists. So, we're given that we want x prime y. Okay, this is gonna be a lot of algebra to prove that it's correct, so follow me, please. Let's have our inverse ready, because as you saw, in both ways, we needed inverse. So in the first way, we needed like the first step. In the second, we needed more like on the last step, but well, we need an inverse. And for this function, an inverse will look like x cubed squared over 27 minus 2 over 3. Okay. If you don't agree with me, well, first of all, obviously you don't agree with me. But if you don't agree with me, it means that you got some problems with finding an inverse, and I'm sure if you take your time, you'll see it. I just don't want to show step by step how we got it. It's the same. Let's express x in terms of y. Perfect. So, I'm going to first now use the second way. So, go ahead and finally use the inverse function rule. And you remember that yesterday you got it. So, we were saying, so now way 2 I'm using. So, first, y prime x, since yesterday you should have it, it is a fraction, numerator 9, denominator 2 square roots of 3x plus 2. Okay, perfect. So then we know that an inverse function rule works, so we can write it first of all like this: 1 over y prime x, so that will be equal to a fraction of 1 over this whole thing. And let's make it a bit better. You know, 1 we divide by a fraction, so after the division, what we're supposed to get is 2 square root of 3x plus 2, and in the denominator we're getting 9. Okay, is that okay? So far so good? We got it yesterday. Okay, more pluses. Okay, well, yes, perfect. So, what we should do now will be our second, well, actually, last step for the inverse function rule. We are going to substitute this, so replace x with its expression in terms of y. Okay, so now we don't actually know yet the real answer, so we're just trying to use inverse function rule step by step, and then we will prove that it's actually the same thing, so use y1. Okay, so I'm going to write it. There will be a bunch of steps. So first of all, I'm going to copy this. Okay, and now instead of x here, I'm putting all that. So this is supposed to have parentheses. Okay, so see what I've done. I just replaced x with its expression. So given you have two x's, for example, given we had here afterwards something like plus x, we were supposed to replace it as well. Okay, luckily we just have one x, and let's work with it a little bit, because otherwise we're not gonna see the beauty. So the beauty here, now the first thing that I'm gonna do is multiply 3 by the thing within the square root. So the square root stays in place, and then after the multiplication, what I'm going to have is y squared over 9. This is 3 times this. We then can simplify 3 minus, then 3 times 2 over 3 gives me just 2, and then I have this plus 2 that is not going anywhere. I have to write plus 2. Okay, all this is over 9. Whew. Now I can see this first of all gives me 0, and then I end up with a square root of y squared over 9, and I can't take this square root. So I'm gonna have my new fraction 2. This 2 is just this 2. So it was the coefficient since the beginning. It was this 2 here, this 2 here, didn't change. And now the square root, I know that I can extract it. So I'm ending up with a fraction y over 9. Okay, let me just check real quick if yes, 1 over 3, right? Not 9. Okay, yes, perfect. I see you following. And over 9, y over 9, but just because there was this over 9. And this is equal to 2y, this is equal to a fraction of 2y over 27. Okay, so we got something. We got this just following blindly the inverse function rule. So we found the derivative ugly. Now we're going to find the derivative of actually x in terms of y, and you already see that it will be this. So let me just write it here so we have our notes pretty. Way to find a derivative of an inverse that we already have. So this one, right? Okay, well, not that difficult to see that here x prime y equals to 2y over 27. Over 27. And of course, this example is showing you that much simpler is our way 1, because finding an inverse here was not a rocket science, and finding its derivative is not at all. Unlike way 2, where finding the derivative was then we were supposed to do 1 over that, so we could make 100 arithmetic mistakes on the way to get here. So obviously, if you're not asked to use inverse function rule, especially in this case, you are not supposed to do it, because it's significantly complicating our life. But it works. That's all I want you to know. I want you to believe me, and obviously you don't believe me just like that. So here is the proof. Okay, perfect. Case closed. Now let's move on with our presentation. So I corrected it, so here now you have y, not f. And this is going to be very fast right now. So, because it's not that difficult. what is the difference between derivative and differential. So let me just write it here. So first, derivative of y of x is what? We write it for now as y prime x, and it is equal to dy dx, where we can think of dy and dx as increments of y, increments of y and x. Maybe like that. Okay, it's not like I have a obsessive compulsive disorder, but I just want you to have this clear. Okay, perfect. So this is the meaning of derivative, right? We were always saying that it is a rate of change, right? So it shows us how y changes given a certain change of x. And this is the rate of change. So here it's the rate of change of y. So differential. Well, differential is just this part of y. Let's write it. Differential of yx. It's dy, and it equals to, from here it's very easy to see, y prime x dx. So that's it. Nothing more complicated here for once. So what is that? We know that dy, dx are just increments. So differential, it's just the change. So the increment part only. And you will see, well, right now with one variable it's not as impressive, but when we will get to our total differentials, you'll see where we can actually use it in economics. So when we have many variables, sometimes we don't want to know the rate of change. We want to know how my, I don't know, investment changes if consumption, stupid example, how my GDP changes if consumption changes, investment changes, and government spending changes. Like they all change at the same time, and I don't want the rate of change, I want just the change itself. And here is where we use total differentials. So in multivariable cases, it is very important. Then in ISLM model, it is used usually, but last year in our macro class we didn't go that way. We were talking about it in a little different manner. Maybe this year we decide to add differentials to our macro, maybe no, but just for you to, you know, sense this rate of change versus change. That's why I'm showing it here. And in micro you will not have it almost at all, maybe only in some theoretical part. So this is very simple, and this is not gonna be a big problem neither right now nor later. So just, you know, don't focus much on this part right now. Let's do the exercises. What you have to understand is what's the difference between the two, and believe me that for multivariable cases and the long models, this can be a real well, helpful method. Okay, so let's find it. And last time I showed you how to do it with an example. So I'm giving you right now like really 3-4 minutes, and we're just gonna write it down together. Okay, so here we go with the solutions. I'm going to really do it like simply, the very first stage. So what do we have here? We have a product, so that will be 4 times 3x minus 8 power, no, okay, so I'm slowing down, cube plus 3, actually 9, 3x minus 8 squared times 4x plus 3, all that times dx. So this derivative is showing us the rate of change, right? So by how much y increases when x increases by 1. And dx is actually the increment of x. So if this is equal to, I don't know, 3, then we multiply it by the rate and we get the change in y. Makes perfect sense, right? And sometimes that's what we have to do when we are asked just for the change in y. Okay, and then for the second one, well, you know, this is our quotient rule, and we ending up with denominator squared, so that's gonna be to the power of 4. And then here the derivative of the numerator is 1, so I'm just gonna rewrite the denominator as it is for the first term, and then minus the derivative of the denominator is gonna be 2 like 4x, and then here I'm gonna have this nothing. Okay, is that good? Is that good? No. Yeah, what's up with 4x? The derivative of the denominator is 2 times x squared plus... yeah, we have to... Wait now. I'm gonna write it all. 2x plus 1. Now it's good, right? It can be simplified and then done. It can. Okay, cool. Yeah, well, we see here that this is factoring. Yeah, okay, but this is correct, right? And then we have to add the x. Yes, all good. And then for the last one, real quick, We have again a product. So for the first term, we're gonna have ln of 3x plus 2 squared. And for the second, we're gonna have the derivative of this ln So squared is just the inside part. So the first, this is a chain rule for the logarithm. So we're gonna have 1 over 3x plus 2 squared. And then we're gonna have this multiplied by, well, let's write it with times. So it looks like a step-by-step times 2 3x plus 2 and then times 2 again. Times 2 again. Times 3 though, sorry. And then we're gonna put big parentheses and dx. Give me a plus or minus. Okay, check. Yeah, you could obviously simplify it and your final answer would be much better, but for the first stage it is like that. And then we do the, yeah, well, here certainly we have 6 and then we don't have this square. Okay. The x is missing, where 9 comes from in exercise 1. Okay, first let's see where 9 comes from in exercise 1 and then let's look for the missing x. Okay, so here this 9, this second term here, it is the second part of the product rule. So it's supposed to be the derivative of this part, the second, times the first parenthesis. So the derivative of the first part is 3 times this whole thing squared, but then times 3 again. Because 3 is the derivative of the inner function for this case. So this 9 is actually composed of 3 times 3. Okay, so yeah. Okay, the missing x. Wait a second, don't tell. Okay. It's just that the first product is missing. Ah, yes. You're right. Where does the last 3 comes from? So let's consider first of all this thing before x. That's what I always forget, so you could already notice it. And I told you don't forget it. Well, this is how it works. Okay, so let's consider this big part. What we were taking is the derivative of a chain, so the derivative of the log of blah blah blah, right? So first of all, it was a square. First of all, it was a logarithm that we were supposed to derive because it was the outer function. The derivative of the log is 1 over whatever it is inside the log. Perfect. Now we can breathe. Then the inner function for the log was the square of parentheses. So the square results into 2 times the whatever it is to the power of 1. Perfect. And then there is another inner function. The final one is 3x plus 2 and its derivative is 3. So that's where the last 3 comes from. Is that good? Chain rule, exactly. Perfect. And then this x, we were supposed to multiply, not forget it, because we're still inside the product rule actually, right? So we were supposed to multiply the derivative of the second by the first, and the first is just x. Okay, perfect. So I gave it to you to train your derivative skills again, because after all, we can call it whatever, differential, we can call it the inverse function rule. Well, what you have to do everywhere is to take a derivative. Okay, got it. Perfect. Thanks. Moving on. Whew. Partial derivatives. Okay, this is something what you probably were struggling with when we were talking implicit function. So let's see now the little theory behind it. Well, it's not theory, it's just logic. Okay, so given a function with many variables, so x1, x2, blah blah blah, or in our case we always have x, y. In order to calculate a partial derivative of this function with respect to one of the variables, we will treat other variables as constant. So look, this notation is now appearing. Partial derivative of function with respect to certain variable. And what is the sense of it? What is the sense of partial derivative? It is a rate of change of a function given one variable changes by one, others staying equal. So this is your ceteris paribus clause from economic theory, other things equal. So for example, if I just want to know how an increase in income influences my demand, the value of my demand, well, I take a derivative with respect to income, other things staying equal, like price of the good not changing, whatever else, price of the other substitute good not changing, price of complement not changing. So I am separating the effects, and sometimes it can be very helpful. And in, for example, econometrics, you will see that that's how regressions work. We always see how our dependent variable changes when one independent variable changes and the other staying equal. Okay, perfect. So this is just to train. I'm gonna give you here 7 minutes because you see how beautiful the last ones are, and then we're gonna check it together as fast as possible. So here you go. You have your, what did I say? 8 minutes, 8. So we're gonna check it at 10 minutes. So when it's 4:10 in Paris. Okay? We'll get partials with respect to, let's see, with respect to what? Well, I was thinking, let's find partials with respect to everything, but let's just do it with respect to x for now. Okay? So now your task is find partial derivative with respect to just x, and then we'll see, maybe for some of them I show you, like for example for the second and for the third they are symmetrical, so it doesn't make much difference, and for the first we can actually calculate both, but let's just do for now x with respect to x. So you're treating y as constant. Y for us is again just a constant. So notice that I'm using this notation because we should get used to it. I obviously prefer g prime x, and if you're taking the derivative with respect to y, you will write g prime y. That's faster and nicer, but this notation is used in many textbooks, and you will see it very often. In some micro, in some micro too. Okay, perfect. So now this third, well, let me first rewrite the third thing like g or this is technically g of x and y, and it is equal to e to the power of e times x squared plus y squared to the power of minus e. Do you agree with that? So you could do it or not, but I prefer doing it because I see that now, well, I have my e to the power of e, it's just a constant, so first thing I'm gonna write it here, and then I'm not dealing with this as with a fraction, and I'm not even using any, well, I'm using a chain rule, but just one step. Okay, cool. So taking the derivative of this with respect to x, treating y as constant. So first of all, we're gonna get the derivative of the outer function, which is an exponent. So we're gonna end up with something like this. To the power of minus e minus 1. And then what's left is the derivative of the inner function, which is just 2x. Okay, is it good? 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 Okay, super cool. Now we're moving to the fourth. And here, what you have is the so-called constant elasticity of substitution function. So if your goods are x and y, and this is a utility function, then this utility function will have constant elasticity of substitution. That means that no matter how units of goods y and x you already have, the substitution rate will always be the same. Okay, well, let's see. The derivative of this function with respect to x will be, well, first of all, it's a fraction of 1 over alpha. Then times this whole thing sorry, x to the power of alpha plus y to the power of alpha, and then all that to the power of a fraction of, so we have to do 1 over alpha minus 1. I think the third one, what is missing? What is missing in the third one? Something can be very well missing. What is STH? Something something a little big is missing. Wait, I took the derivative. Well, what is missing? Is something missing? Oh, you can unmute and pronounce it.
Okay, so sorry for that. But I think that in the last, the solution in that is the derivative of g to the fraction of g, the g prime to the x, is e squared times parentheses the fraction of e to the denominator x squared plus y squared, and all of that, parenthesize all of that to the power of e minus 1 times a fraction of minus 2x derived with parenthesize x squared plus y squared squared, the whole of that. That's my debate here, my argument.
Okay, do you agree with this? That we can rewrite it this way? Then you don't. Yeah, I suppose that the outcome will be the same. It's just that, first of all, I didn't like e squared. Because it should be e to the power of e. Okay. Well, you should have e to the power of e. Well, Lucas, tell me, first of all, do you agree with this? That I can rewrite a function this way? Dun, dun, dun. Because if you agree, then we just might have gone different ways of derivation. Okay. Then we're good on that? Good plus. Okay. Okay. Let's move on to our fourth. So 1 over alpha minus 1 will be 1 minus alpha over alpha. This is the derivative of the outer function, so we have to multiply it by the derivative of the inner function, which is x to the power of alpha. And then we get x to the power of alpha minus 1. Wait a second, I'm gonna show it completely. So something like this, and then we can get rid of the denominator because alpha and alpha go away, and then we'll see some nice features about this. Perfect. And then the marginal rate of substitution. For the marginal rate of substitution, what you have to do, you have to then get the derivative with respect to y, and then you divide one by another, and you see that it all cancels. Perfect. So that was for the partial of x, and you will have to do this exact thing many times, because then you'll have to find the optimum, and for the maximization you need partial derivatives. Could we also write to the power of? Yes, you could also write that. It's just that for some next potential steps that I'm not asking here for, you might need this form of the exponent, but totally okay, you could leave it as 1 over alpha minus 1. Okay, perfect. Then the last one, something not super nice. Well, it's just going to be a big fraction, right? So we're treating everything other than x as constant. Where is that? Here. All of that squared, and then for the numerator, okay, follow so I don't lose anything, 1 over x times all this minus 2x times ln x plus sinus plus e to the power of the z. Good? Maybe. Okay. 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 Perfect. So that was a little exercise for partial derivatives. You see now you're getting more and more used to treating other things as constants. That's great. Total derivatives. Okay, so what is that? Partial derivative is when we only taking the change with respect to one of the variables. I told you keeping other things equal. Total derivatives allow us to to still have some sort of rate of change when one variable changes, but what we have in mind is that this variable can be an argument of a function of another variable. So blah, blah, blah. Here with an example it's better. Here you see something that is written in terms of x and y, right? So if we just treat x and y as absolutely independent things, then total derivative does not make much sense. Because if y does not depend at all on x, then we can just take a partial with respect to x. But what if there is an underlying relation between x and y? And maybe some of you who took econometrics remember about this inverse causality that, well, we can think of what happens, not inverse causality, sorry, multicollinearity, when one variable is actually correlated to another variable, and this is messing with our calculations. So for the total derivatives part, total derivatives allow us to take into account that underlying relation between x and y and get the actual rate of change of the function when one of the variables changing and also causing the change in the others. So let's write here the total, wait a second, don't calculate anything just yet, total derivatives, and I'm gonna give you an example. So here technically we also have two ways to do it, and maybe this way with the formula is going to be trickier and not gonna simplify our life. So let's take an example that I will do. We have some function g of two variables, and it's gonna be e to the power xy plus 3x squared y. Okay, so I know that there is an underlying relation between two, and it's like that. So you obviously not always have that information, first of all. Or you can even have a case where they're not correlated at all and you can say it for sure. So this total derivatives is a specific technique for a specific case. Okay, so when we have an expression, a functional form of y in terms of x. Alright, so we could just straight replace, so way one has two steps. Replace y by x squared. Find g prime x. You will see that whenever we replace all y's with x squared, we end up with a function of one variable, and well, we can just find the normal derivative, and it will be total derivative because we don't have any second variable. Okay, let's do it, and then we use the rule, and then we will prove that they give us the same results. So if we replace, we're ending up with just g from x, and it will be e to the power of x cubed super cute then plus 3x to the power of 4. Okay, easy. So g prime x is equal to 3x squared e to the power of x cubed plus 12x cubed. Okay, I'm not even asking you to prove it, to check it, because I know for a fact that it's correct. Okay, perfect. So that will be our total derivative. So now please pay attention to the notations, because when we use d, this is always for total something. When we had just one variable function, well, doesn't make much sense to differentiate the total and partial, because the only variable we had was x. Now when we have two, we have to make sure we use correct notation. So d for total and this weird thing for partial. And note that if we use my favorite g prime x, it will have no difference, because, well, I can use g prime x for the total and I can use here g prime x for partial. So just make sure that you don't use, for example, partial for total, or you don't use total, which is worse, for partial. If you want to just avoid this problem, you can use this notation, g prime x, and that will work for sure everywhere in your micro exam. Write it, you will have utility prime x, utility prime y, no problem. Okay, so that was way one. Way two. As always, I'm showing you something that is more complicated, but this is a theory that I have to prove you right. Okay, so for way two, I have to use the formula. Okay, use the formula. Okay. And then, unfortunately, step two, replace y, replace y with I replace y with x squared. Yeah. Okay, so you see, it does not make much sense, because after all, you have to replace it. But let's just see that it works. Let's just prove it. Okay, so I'm going to use again this notation as well as on the slide, so you have it with an example. This total will be equal to g prime x, here I mean partial, so let's find it straight. So the partial derivative of this thing with respect to x. So that will be y e to the power of xy plus 6xy plus 2 plus 2x times x e to the power of xy plus 3x squared. Again, I know that it's correct, so if you didn't have time right now to follow through, you have this note, so make sure that you agree with my derivative. Okay, so we got a long expression. Nice, cool. That was the first step, use the formula. And okay, let's mark that this is the first step and this is the second step. Here, this is the first step, and the second step will be yeah, we cannot do much. The second step will be replacing our y with its actual functional form. So all this is already, I have to explain, I didn't explain here. What is this? So this first is a partial, look at the slides where I'm showing, a partial of g with respect to x. That you have to be agree with. Then we have a partial of g with respect to y. And that's that. So remember, this is the function. So the partial of it with respect to y will be this. And then in the end, we are adding 2x, which is the total the derivative of y with respect to x. It's total because y in terms of x just have one variable. So that's that. Why xy and not 6xy? Because it is 6xy. Thank you. Okay, great. So now it has to be clear. So this is first part of the partial with respect to x of the initial function. This is the partial with respect to y of the initial function. And this is the derivative of y in terms of with respect to x, because we were given this part. If we are not given this part, we can do nothing. Okay, perfect. Let's do the replacing. So that will be x squared e to the power of, here you can see that it will be x cubed because it is x times x squared. Well, that will be x cubed. Then we will have 6x times x squared, so 6x cubed. Then we'll have, let me do this multiplication straight. So we were supposed to end up here with 2x squared e, so like 2x squared. This is just because I multiplied this by already 2x. 2x squared e to the power of x cubed. Again, here we had this and I substitute y by x squared plus 6x cubed. This is just this times this. Okay, great. We can see obvious potential for simplification. Okay, now it's straight. And we have 3x squared e to the power of x cubed plus 12x cubed. And it is the same as we got using the normal simple technique. Okay, so again, this is to show you that the formula works and it actually makes perfect sense. It is a little bit of the chain rule logic, right? So here, this is just a chain rule application because we take the derivative of the outer sort of function for y and then multiply by the derivative of the inner sort of function of y. Okay, so now I'm going to give you also some time. I forgot, when did we start? We started at 4:31, so okay, just enough time. Let's check these total derivatives. You know what? Do just first three. I don't want to do the last one because it's too heavy. Okay, a small clarification. Yes, go ahead, unmute.
Yeah, in the slide where you're explaining total derivatives, you said dg dx is equal to del g del x plus del g del y into dy dx. I wanted to know, shouldn't it be del y del x as in instead of dy dx? Shouldn't it be the partial version? Then del y and del y can cancel out and you'll have del g del x. Because you said that we need to be very careful with where we are using the del and the d.
Okay, but then think of it. Why would it be partial here for y if x is the only variable of y? It's not about canceling thing. It's about chain rule more.
So when we are differentiating with respect to y, here y is just a function of x. So here d and del will mean the same thing as in dy dx.
Yes,
and
yes.
del y del x.
When we're talking about this exact thing,
Exactly.
partial and total is the same because we only have one variable. So the mere notion of partial stops making sense because we use partials when we have many variables, and partial with respect to one, that's what we're taking. So here I actually insist on the using on the use of the total because that's what also chain rule implies, because we have to go to the very final total derivative because we only have one variable. So yeah, this writing is correct, and if you wanted, you could technically replace it with the del, but to me it doesn't make sense because it's more of a total than partial since we don't have any other variables for y here.
Thank you so much.
Okay, you're welcome. So let's do real quick the first three. No, first two. So I am giving you 6 minutes for the first two, and I insist that you use the formula here, because without using formula I am sure you can do it. So replacing at the very first step, so going through way one, just do the formula and we see. Okay, so you have your 6 minutes. Slide what? 13. Partial with respect to x here is very simple. It's 12x plus 4y. And then plus partial with respect to y is also not bad. 4x plus 6y. And we multiply this partial, the second one, by the total of y with respect to x, which is just 14x. Don't we have to express everything in terms of x finally? Yes, we do. So let me go step by step. That was the first one. And now, instead of y, I'm going to write 7x squared everywhere. So this will stay as 12x plus, okay, thank you, Robin, I'm not gonna do that, but for those who got the final answer, well, you can check. So here we had 28. Okay, look, everything is good. You guys move on. Okay, so here x squared plus, okay, got confused. Plus here 56x squared plus then we're going to replace y by x squared. So we end up with 6 times 7 times 14 x cubed. And it looks good to me. Yes. Yes, looks good to me. Perfect. So that was the first one. And if you just replaced y on the first initial step here, maybe it would be simpler. I don't deny it. But just understand the logic, what we're doing here. So we know that with the change of x, y also changes, and we want to know exactly why. And then we know that y enters the function g with also certain coefficients, powers, whatever. There is a different functional form for all of them. And oh, that's just because you got mistaken. Because you saw that here it worked, right? You should believe me. It's supposed to work. Okay, great. And now, real quick, the second one. So the partial with respect to x is minus 2x. Then plus partial with respect to y is 3. And then we multiply by the partial, by the total of y with respect to x. And here we get for x plus 1. Okay, so look, here maybe just here for this very example, this is much easier. Because after all, we ended up with no stuff to substitute, right? Okay, perfect. Not checking the second one. Let's move on to the total differentials. And here, as well as just normal differentials, you don't have to do much. You just have to take your partial derivatives and write dx, dy, dz